So again I will ask you this most frequently asked questions. Is my screen visible? Am I audible?
Sir, you are audible.
Okay.
Screen is not visible, sir.
Screen is not
Screen
visible.
is not yet visible. Okay, I will share it again. So I was trying to connect through our college internet, but at present I have connected with my mobile. Sanghani sir, is our college internet is now working after electricity resumed?
No, sir. It is also not working. I have also checked that thing.
Okay, fine.
But I have connected in mobile.
Okay. I will try to share it again. Maybe due to less bandwidth, it is happening. Okay, again I will share. Now is it visible?
The screen is not visible.
No, not visible, sir.
Not visible. Okay, let us wait for a minute. I think if it is visible, then.
Don't worry, sir.
Okay.
Now.
So there is some lagging,
visible.
Right? Some lagging is there. Okay.
Yes, sir.
Yes, sir.
Good afternoon to all. Today we will discuss medical image analysis using wavelet transform. And this will be our discussion topics. We will look at the introduction of wavelets and wavelet transform. We will also look at signal and image representation using wavelets. So session is although image analysis with wavelet transform, but we will also discuss the signal, because there is not a much difference between the signal analysis and image analysis with help of a wavelet transform. In signal case, we will be looking at one dimensional, and in image processing, we will be looking it as a point of view of two dimensional. We will also discuss multi-resolution analysis using multi-level wavelet transform. Then after implementation of discrete wavelet transform of signal as well as image. We will also look at Python program for analysis of digital image. I will also show you how to write the program to analyze the signal. We will also look at one program of denoising a digital image as well as a signal. I will repeat this portion. Maybe all of you are very much familiar, but it will be useful to those who are not familiar with the wavelets. So some part, I will be looking at the introductory part of wavelets. What is wavelet and what is wavelet transform, and basic mathematics of the wavelets I will discuss first. So before that, what I will do, I will put this in a local loop so that I can also see that whether slides are visible or not. Usually I do in my lecture. So usually, I take the local loop kind of a thing, so that exactly there will not be any lagging between the slides and the discussion. That's all. Yeah. Just for 1 minute. Okay, I think this slide is visible now. What are wavelets?
Yes, sir.
Okay.
Visible.
Okay, fine. Wavelets are basically oscillatory functions, and they are vanishing outside the small interval, and that's why it's called wavelets. As the name suggests, that wavelet means a small fraction of wave, and that's why the name wavelet is given to it. So ultimately, we all have studied the Fourier transform. and Fourier series. We are using Fourier series to represent any signal or image. Similarly, we can also use the wavelets to represent any signal or image. So wavelets are basically a building blocks of the signal or image. Wavelets are the functions which are well suited to expansion of real-time non-stationary signals. So basically the Fourier transform is good for a stationary signal, but somewhere it fails for a non-stationary signal. So in that case, wavelet is very much useful. Then wavelets can be used to decorrelate the correlations present in the real-time signal, such as speech, audio, video, then biomedical, seismic, etc. So for all such signals, the wavelet is very much useful to decorrelate the correlations present in the signal. If you look at the properties of the wavelet, wavelets have a compact support. That means most of the energy of the wavelet is restricted to finite time. That means wavelets are localized in time or a space. And another very nice property of wavelet is that it is also localized in frequency. So localization in a frequency domain as well as localization in a time or a space domain. If you look at the signal, then in time domain. If you look at the image, then it is in a space domain. So it has both the localization simultaneously. Ultimately, it's otherwise very difficult to get both the localization simultaneously. So this is a very nice property of wavelet. It has a finite frequency band, so limited in time as well as limited in a frequency. The decay towards the high frequency components to the smoothness of the wavelet. So basically, as and when we are taking more number of filter coefficients, the wavelet becomes very smooth. Smoothness increases with the filter length increases, such as in the Debye wavelet. If you use Debye 4, then Debye 8, then Debye 16. As and when you use the more number of filter coefficients, you will get more smoothness. But at the same time, penalty is that you require more computation time. Then question may occur that we have a very good Fourier analysis available with us. Why we should use wavelets? Then Fourier analysis provides a signal spectrum, that is range of frequency within a signal, but does not provide temporal relationship. Like it will not tell us at what time what is the frequency. While the wavelet analysis will provide us time versus frequency representation of the signal, it also provides the temporal relationship. So wavelet analysis is good for real-time non-stationary signals. Wavelets solves the resolution problem of STFT by using the variable length window. So whatever I am speaking and whatever displayed on the slides are in synchronization or any difficulty?
Yes, sir.
No, sir.
It is in synchronization. Yes, then there is no issue, right? Because I am worrying about because I have connected through my local mobile network. That's why. Otherwise, if it is an institute network, then this type of problems normally do not occur, right?
Yes.
So I would like to show this, in a Python program, actually this limitation of Fourier analysis and as well as the STFT. So just I will stop this presentation and will start the Python demonstration with this. I have started the Jupyter notebook so that Jupyter notebook content is visible on the screen.
Yes, sir, visible.
It
Yes,
is
sir,
visible.
it's visible.
Fine. Okay. So this actually program will show you the drawback of Fourier transform. Now in this case, I have taken one chirp signal. So this is actually a command which is specifying the chirp signal. And it has a frequency starting from 10 to 1, so frequency is basically changing. and I'm actually executing this program here. So this is actually our chirp signal, where slowly and gradually initially frequency is high, then frequency is reducing. And if you look at the Fourier transform of these, you will find that these are the Fourier components present in the signal. So it shows the Fourier, what are the frequency components present in the signal. Then what I have done in this program, what I have done this, written the same program, but now my chirp signal is initially the frequency is less, and then with respect to time the frequency is increasing. So the same signal, but the localization of high frequency and low frequency I have just interchanged, and then I am running the same program again. When I run this program, and whenever I am getting this Fourier transform of that signal, you will find that the Fourier transform of both is same, because Fourier transform just displays what are the frequency components present in the signal. It doesn't give any information about where is what, at what location what is the frequency. That analysis is not given by Fourier transform. So this is actually a limitation of Fourier transform, and because of that we are using a wavelet transform. Once again I will start my presentation. So I am back to my presentation. Is the slides are visible?
Yes, sir, visible.
It's visible.
Visible,
okay,
sir.
Fine. So wavelets are basically localized in frequency. It has a finite frequency band, and these are all the very good properties. But apart from that, we use it because it has both the localization. It will also tell you at what time what was the frequency. That's why it will provide you a temporal relationship, and that's why the wavelet analysis is good for real-time non-stationary signals. So wavelets also resolve the problem of STFT. That is, because to solve this problem we were using the short time Fourier transform, but whenever you are using a STFT, it has also its own dilemma. That in a STFT you have to use the fixed size of window, and whenever you are using a fixed size of window, whenever you are using a narrow window, what you will get here is a good time resolution. So if you use a narrow window, then you will get a good time resolution, but you will get a poor frequency resolution. So there will be overlapping in a frequency domain whenever you are using a smaller window. And if you are using a wide window, then you will get a better time resolution, but the problem will occur in a frequency resolution. So because so this is actually, you will not be able to solve both the problems simultaneously. That is actually dilemma of resolution in case of a STFT. But in case of a wavelets, actually we are changing this. We can dynamically change this window size. So we can change the window size depending on the requirements. So that's the beauty of wavelet transform. So as you can see here, that if you are having a low frequency signal, whenever your low frequency components are there, we can use a larger window size, and as and when frequency increases, you can the reduce width of this wavelet function. So by using a different width basically is nothing but your the main property of wavelets. So you will be able to do the dilation in the wavelet. So dilation of wavelet function will depends on the frequency resolution required. So depending on the requirement, we will be using the different dilation factor, right? So ultimately we are not using same window size for all the frequencies, but we are using a different window size for a different frequencies. So that's actually a beauty of wavelet transform. Just for a more clarification, let's understand the properties of wavelet, right? And let's look some mathematics of the wavelet. Is everything fine? Slides are visible?
Yes, sir, visible.
Okay, fine. All right. Let's look at this equation. This is known as a psi jkt is equal to a raised to j by 2 and psi a raised to jt minus k. Now let's understand this equation. So this equation represents that this wavelet is just like a microscope. If you set this j, that means j is your magnification factor. This j here in both the cases is a magnification factor, and this k is basically which satisfies the translation factor. That means it specifies the location where you want to see actually. So if you are interested in a small details, if you are interested in a detail, then magnification required will be large, because it's the same thing we are doing in a microscope. If you are interested in a small details, normally you will zoom the microscope, and because of that zooming you will be able to look at the small details. So in that case we will be increasing basically this j in this equation. So in this equation, basically if you increase the j, that means you are interested in more details. You are zooming the basically object. Now this is a very generalized equation, useful for both signal as well as for the image. In this case I have taken t, that is in time domain, so that's why it represents the time or a signal, and this k is a translation factor. So ultimately, you know, this a raised to jt corresponding to the small steps which are used to catch the smaller details. If you are not interested in smaller details, then you know, you can reduce the j. So ultimately, normally in a binary implementation in a computer program, we take this a is equal to 2. So ultimately this equation will become 2 raised to j by 2 psi of 2 raised to jt minus k. So ultimately it allows us to you know, see the forest and trees together. You know, if you are on a helicopter and you know, if you see you know, the forest, then you will not be able to identify what type of trees are there, whether there are mango trees or neem trees or what are there. Just you will be able to see that there is some forest. If you are interested, then you have to reduce the height of helicopter, right? When you reduce the height of helicopter, that is very much similar as increasing value of j. So basically you are interested in more details. Either you reduce height of helicopter or you take one durbin and then view the forest with help of a durbin, right? So to magnify the details. So ultimately wavelets allows you to zoom at different level, to move at different locations, so that you will be able to analyze each and every details. If we start with a preliminary you know, mathematics, in previous equation, as I told you, for the binary implementation we take a is equal to 2, so you can take a equal to 2. So we will look at initially this function phi jk. This is a scaling function. Again the purpose is same, j will give you a different zooming factor and k will give you a translation. So 2 raised to j by 2 phi 2 raised to jt minus k, where phi jkt covers the entire square integrable space L square r with all possible values of j and k, right? Now let's say, for example, if you take j equal to 0 and k equal to 0, then this equation will reduce to this 2 raised to 0 phi 2 raised to 0 t minus 0. So ultimately it will be a phi t. So at one particular zoom level and at one particular zeroth location, you will get some function phi t. Now let's do some variation. When you fix the magnification factor j, the scaling function will not cover the entire space, but it can cover some subspace. So for example, if you fix the value j equal to 0 in this function phi jkt, we can write this function as phi 0 kt is equal to phi t minus k. So where k is basically a translation factor, because we want to go to the different locations, and for that we are basically changing the k. So we are using one particular zoom level, and using that zoom level for a different value of k, we will analyze the signal. So ultimately, if you can take here k is equal to 1, you can take 0, 1, 2, 3, 4, 5 and so on. And when you use j equal to 1, let's see what is happening. Like when you put j equal to 1 here, what will happen? In this equation, if you take j equal to 1, then 2 raised to j by 2, that means 2 raised to 1. So this equation will become 2, and then 5. Here 2 raised to j, so now j is, you have taken 1, so it will become 5 2t minus k, right? So you have one more next level of zooming if you take j equal to 1. Then when you take j equal to 1, this will become 5 2t minus k. That means now you can analyze the width in a multiple of 0.5. Similarly, if you take j equal to, let's say, instead of 2, if you take, let's say instead of 1, you take a 2, then this will become 40 minus k. That means you will be able to analyze the functions having a width in multiple of 0.25. So that means if you are increasing value of j, you will be able to catch the smaller details available in the signal. Let us understand this concept with the help of function space. Let's say we take this v0. So we have taken j equal to 0 and k equal to 0. So our function is now phi 0 0t, and that is actually represented by subspace v0. Next level, if we use j equal to 1, then our function will become psi 2t minus k. So now the width is less compared to this. Width is half of this, right? So this function, we can say it is a subspace v1. So now in this case, v1 have a more details compared to v0. So whenever you are using j equal to 1, you will get a more details. Further, you can expand this subspace, like you can take one more space here and you can call it as a v2 corresponding to j equal to 2. And if you want still some approximation, then you can also go towards the minus side. You can take j equal to minus 1. If you take j equal to minus 1, then this will become psi of t by 2 minus k. So ultimately, you are not interested in a smaller details. You are going towards the approximation. Similarly, you can go beyond that also. You can go up to v minus 2 also. So in v minus 2, you will get very approximate. So as and when you are coming outside, you are adding more and more details in the subspace. This function phi jk will represents entire L square R square integrable region. So you can see that as and when we fix the magnification factor j, and scaling function cannot cover the entire space, but it can cover the some subspace. If you take j equal to 0, it will cover the v0 subspace. If you take j equal to 1, it will cover subspace v1 and so on. Okay, so whatever again I am asking you, whatever I am speaking and whatever displayed on the slide is in synchronization or not?
Okay, sir. Okay.
Okay. Because in my mobile, lagging is there in mobile. Maybe because of the network issue, right? Okay. Yeah. Third level of approximation, you have to choose the value of j. Yeah. If you are not satisfied with the level of details what you require in a v0 subspace, then you can add the details like j equal to 1. Then it will cover the next subspace v1. Still, if you are not satisfied in the detail, and if you want to further zoom it, you can put j equal to 2. You will get the next subspace v2. You will be getting more and more details as per the requirement. But again, in both signal and image analysis, you require more number of bits to represent the signal or a image. As and when you are moving from v1 to vn, you will require more number of bits to represent the signal or a image. So it depends on the requirement. If you are satisfied with the approximated version, then you can choose the lower level of geom value, that is j equal to 0. So you can start with the j equal to 0, then you can go up from j equal to 0 to 1, 2, 3, 4 and up to n. Similarly, you can go downside -1, -2, -3 and up to -n also, right? So if you take j equal to -1, it will cover the subspace of V minus 1. So V minus 1 is a subset of V1. Basically, it is a subset of V0, then V0 is subset of V1, V1 is subset of V2, V2 is subset of V3 and so on, right? So ultimately, mathematically, we can specify it in this way. V minus 2 is a subspace of V minus 1, V minus 1 is a subspace of V0, V0 is subspace of V1, V1 is a subspace of V2 and so on. And if you want to represent in this way, union of all Vj, where j belongs to z, is actually equal to L square R, entire space. Okay, then let's look at this. We can represent the scaling function of subspace V0 by scaling function of next higher level subspace V1. So as you know that this phi t is a scaling function of one subspace V0. Okay, then phi 2t minus 1 phi 2t minus 2 and so on. So in generalize I have written it phi 2t minus k. What will be this subspace? It will be the next higher level subspace. So it will be a V1 because it is having a more details compared to the V0 subspace, right?
V0.
V1 have a more details compared to V0. Next level also you can go, instead of this 4 2t minus k, you can also take 5 4t minus k. Then it will become a V2. If you take 5 8t minus k, V3. 5 16t minus k, V4 and so on. So depending on the required details, you will be using the different functions. Okay, now let's look at how it looks like actually. Very basic, wavelet is a Haar wavelet. In a wavelet domain, people start with a Haar. In microprocessor domain, people start with either 8085 or 8051. So in a wavelet domain, people always start with a Haar scaling function. It's a very nice function to study. Unfortunately, it is not practically useful, just like 8085. People start studying from 8085, but in industry it is not useful. Similarly, Haar is also the similar case. Haar scaling function and wavelet functions are good for study, but performance is not that much better compared to other wavelets. So if you look at a Haar scaling function, phi 2t if you take, phi 2t minus 1 if you take, and if you combine these two, then it becomes a Haar scaling function. So this is actually a Haar scaling function. Let me point it here. So this is actually phi t equal to 1, where amplitude is 1 from 0 when time is from 0 to 1. At that time output is 1, and then after output is a 0. So it is basically a Haar scaling function. And if you say that this is a phi t, then what is phi 2t? Phi 2t is this, right? Having a more detail. And now, it must be clear to you what should be the phi 4t. Phi 4t will be here. Width will be half. Then phi 8t will be here. So you are moving towards the more and more details. If you are interested in more details, you will be making this width half. That means you will be increasing the value of j. Right? Ultimately, this is nothing but a 2:j. I am taking here value of j is equal to 1. Here also I am taking 2:0, so j is equal to 0. Whenever I am saying phi 4t, that means I am taking j equal to 2 and so on. But the problem will be that your energy level will reduce. So whenever you are making width half, or whenever you make width double, energy will change. We want to keep the energy same, and that's why there is a role of so there is actually a role of energy is there. Okay, let me put my mobile in silent mode. Okay. Otherwise, it is I am connected with a mobile. So if I will not put it in silent mode, and if I pick up the call, then your network connection will not be there. So whenever you are actually decreasing the width or increasing the width, the energy will not remain same. And to make sure that energy remains same, we are taking coefficients here. So there are filter coefficients as well as there is a normalization, right? So we can take these filter coefficients here in this way. If you take root 2 into h0 phi 2t plus root 2 into h1 phi 2t minus 1, if I take this h0 is equal to 1 upon root 2, this h1 is equal to 1 upon root 2, then this equation will become phi 2t plus phi 2t minus 1, that is equal to phi 2t. Sorry, that's equal to phi t. So you will be able to achieve this implementation by this way, and in this case this h0 and h1 are known as a filter coefficients. So these are known as a Haar coefficients for a scaling function. So it will be h0 is equal to 1 upon root 2 and h1 is equal to 1 upon root 2. So if you want to implement this, you have to take these filter coefficients. Now let's switch over to the detailed subspace. We were discussing that you can move from V0 to V1. And naturally, if you want to move from V0 to V1, you have to add something, So you have to add something here. Some details you have to add. And to explain this, what I will do, I will start actually, let me start something. I will start a Google Map. I think Google Map is the best application to show for this purpose. We can also use some image to show this, but let me start a Google Map. That will be better. And let me search this VP Engineering College. Okay, now it is showing something like VP Engineering College. Is this visible on your screen?
Yes, sir.
It's visible. Okay. VP Sports
Yes,
Ground,
sir,
VP Engineering College, Ram Bakery. So if we consider this as a V0 space, right? And then if you want to move to the V1 subspace, we have to go into more details. So now this we can say it is a V1 subspace. We are getting more details. Let me click on this satellite. Then it will be more clear. And now you can see that this VP Engineering College entire layout is visible. Different buildings are visible, ground is visible. So we can say it is a V1 subspace. Further, if we zoom to the next level, then that means we are going to the V2 subspace. Then more data will come. More data will come and you will get more details. So ultimately, whenever we are moving from V0 to V1, we are adding some details. Whenever we are moving from V1 to V2, then V2 to V3, basically we are adding the details. And whenever you are moving from V2 to V1, basically you are reducing the details. So in this case, only the approximations will be available. Right? Further, if I go to the V minus 1 side or V minus 2 side, only entire view will be available. further if I move downwards, then I will only get the approximated view of VVP here. And if I further go to the V minus 2 or minus 3, minus 4 side, only this method is visible here. Some point is visible here, but not more details about the VVP available. So for a reference of VVP Engineering College, I think we are at the level of V minus 5 or minus 6 somewhere. If we go to V minus 4 to V minus 3, we are moving closer to the VVP, and then after this is a V0, then V1, V2, V3, V4 and so on. So that means now you can see computer engineering department, nanotechnology department, everything is visible here. That means the details are added into that. So that means, okay, I don't know why I am getting this slide. Okay. Okay. All right. So this is actually V0 subspace, and if you add some details in that, we will get the V1 subspace. That means we are getting more and more details in that case. So ultimately we are adding something here. Into V0 we are adding something to get the V1 subspace. Similarly, whenever we are moving from V0 to V minus 1, then we are removing some parts here. This part we are removing, right? So this part we are removing, these details we are removing to get the next level of V minus 1. Similarly, after this there will be a V minus 2. And suppose from V1 if you want to get V2, then also you require to add few more details. Right. So now let's look at. Whenever you have a V0 subspace and you want more details, basically you are adding something and let's call it as a W0. So W0 is one more space which we add into the V0 to get the V1. Similarly, this will be a W minus 1. So V minus 1 and W minus 1, if you add both together, you will get a V0. So ultimately, this will be, overall picture. This V minus 1 and W minus 1, if you combine, you will get a V0. V0 and W0, if you combine, you will get a V1. V1 and W1, if you combine, you will get a V2. Similarly, V2 and W2 will be combined, you will get a V3 and so on up to Vn. So ultimately, idea is that wavelet allows you at what level you want to work, at what approximation level you are interested. If you are interested in more details, you add more layers of W's there. So that's actually concept of a detailed subspace. So function contains in a V1 but not in V0 can be represented by detailed subspace W0, where W0 is a difference between the V1 and V0. So in other way, we can say that V1 is a union of V0 and W0. When you combine the details available in V0 as well as you add some more details which is available in W0, you will get the next level of subspace V1. Similarly, in a V1, if you add W1, then you will get a 1. So ultimately, you can write in this way, Vn is equal to Vn minus 1 added with Wn minus 1. You can expand this in this way. W0 and V0 when you combine, it becomes V1. Then when you combine it with a W1, it becomes a V2. When V2 is combined with a W2, it becomes V3 and so on. You can reach up to the Vn. So this is basically how you will get the V1 by adding the content available in V0 as well as content available in a W0. This discussion is true both in case of a signal processing as well as in case of a image processing, both. So this is the basic mathematics. So naturally it will be applicable to both. And if you further this decompose this V0, you can always do like this: V minus 1 combined with W minus 1. Then further V minus 1 also you can do like this, v minus 2, w minus 2. So ultimately, entire space can be represented by wj, union of wj, where j is from minus infinity to the plus infinity, right? That means this w is basically a subspace which represents our wavelet. That means any signal or any image can be represented with help of a wavelets. So initially we were looking at psi jk function. That was related to v0, v1, etc. approximation subspace. Phi jk was related to v0, v1. But there is another very good function, psi jk, very much similar to scaling function, but it is directly related to w0, w1 subspace. So we can say that this is our wavelet function, mathematical representation of wavelet function. If we take j equal to 0, it will represent subspace w0. If you represent j equal to 1, it will represent subspace w1. If you represent j equal to 2, then it will represent the subspace w2 and so on. So ultimately, this j will be again a zooming factor, k will be a translation factor to move at different locations. And we will call these functions as a wavelet functions. Okay, again let me take the feedback. My slides and voice both are clear?
Yes, sir. Both
okay,
are clear.
Fine. If you look at the additional properties of wavelet functions, translated version of wavelet function should be orthogonal to original wavelet function. So orthogonality is very important, right? Oscillatory nature, some parts should be positive, some parts should be negative, and area under the wavelet function should be 0. So any small wave you take, and then you cannot call it as a wavelet. So wavelet should satisfy these requirements. Okay. Now let's say we have a phi psi t here, and this is actually psi 2t minus k here. Can anybody tell me where I should write w0 and where I should write w1 or a v1? Scaling function is directly related to v1 and wavelet function is related to w0, right? So if you have a psi 2t minus k functions available, you will be able to calculate the wavelet function out of it, right? So I can say that this psi in w0 subspace
W.
and phi 2t minus k will be in a. If you take here psi 2t, then it will be a w1. If you take psi 4t, it will be a w2. If you take psi 8t, then it will be a w3, and so on, right? Okay. So this is actually a Haar wavelet. So initially we told we have seen the Haar scaling function. So there are two things. One is a scaling function and another one is a wavelet function. If you remember the scaling function, it was like this. It was in this way. It was a phi t, right? Phi t was in this way. But psi t is described with this equation. Psi t is equal to 1 for the interval 0 less than t less than half. So up to this interval it is a 1. And then after from half to 1 it is a minus 1. Right. So ultimately you will be able to get, if you have a psi 2t and psi 2t minus 1, you will be able to get this, if you have a phi 2t and phi 2t minus 1, you will be able to get the psi t. Right. So because psi t is nothing but a phi 2t minus phi 2t minus 1. Right. So ultimately you will be able to represent mathematically in this way. Psi t is root 2 of gk phi 2t minus k, and if you expand this, root 2 g0 phi 2t plus root 2 g1 phi 2t minus 1. And ultimately here the g0 will be 1 upon root 2 and g1 will be minus 1 upon root 2. So these are known as a wavelet filter coefficient for a Haar wavelet. This is another representation. If you have a psi t in this way, then if you reduce the width by half, it becomes psi 2t. Right. If you further reduce the width, let me take one more color. If you take a waveform in this way, then it becomes phi 4t, right? Psi 4t. And further if you reduce, it becomes phi 8t. So if you are interested in detail, basically you will be increasing the zooming level j, and when you increase the zooming level j, here you know it becomes 2, then 4, then 8 and 16 and 32 and so on. If you remember, you are using Fourier series to represent any signal. Similarly, you can also use the wavelet series to represent any signal. So this is actually a function which you can use to represent any signal. So let's say you have a function f0t at approximation level 0 in a V0 subspace. You can represent it with this formula, where psi is actually your wavelet function, d is a detail coefficient, phi is scaling function, and c is a Courser's coefficients. So if you combine these, you will be able to represent the signal. Similarly, signal can be also decomposed into different Courser coefficients and detail coefficients with help of a wavelet function as well as wavelet scaling functions. During the implementation, it will become more clear. Again, the same representation. This is basically f minus 1t at the next level of approximation. If you say that this is in a V0 subspace, then this is in a V minus 1 subspace. In a V minus 1 subspace, you are adding some details, right? So this will be a W minus 1 subspace. This is W minus 1 subspace, and this is a V minus 1 subspace. When you combine, it becomes a V1 subspace. So ultimately, what you can do here, you can represent this as a f minus 1. So this is a function in a V minus 1 subspace. And when you add the details in that function, you will get a more details in f0t. So this will be in a V0 subspace. Further, if you require more details, you can add more details, of course, to get the function in a next level. So ultimately, you will be able to represent this f0t. If you further decompose it, if you continue this process, then ultimately you will be able to represent this function with help of all wavelet functions, right? But this is not desirable because it will require infinite amount of calculation. So always you have to start with some approximation, and you have to always start with some approximation. And approximation is a part of life. This is how a more generalized representation of any function at any level. So you can see that if you want to represent ft, then with help of a Courser coefficients and scaling function as well as detail coefficient and wavelet function, you will be able to represent the signal. And then whenever we calculate, whenever we analyze, our ultimate goal is to find out Courser coefficient and detail coefficients, because wavelet scaling function and wavelet function is known to us. Sometimes this scaling function is also known as the father wavelet, and this wavelet function represented by psi jk is also known as the mother wavelet. So both father wavelet and mother wavelet is known to us, and from that signal is known to us, and so our job is to calculate the coarser coefficients and detail coefficients out of it. So ultimately, why we are doing all this job? So ultimately our purpose is that we want to analyze either signal or an image. So multi-resolution analysis is basically our purpose. So ultimately any signal or image you can separate it out into a principal part and a residual part, right? Principal part can be thought of as an output of a low pass filter. It represents the approximation of the signal or image. Residual part can be thought of as output of high pass filter, and it can represents the detail of the signal or image. So ultimately graphically if I show, it is something like this. Discrete wavelet transform of any function, you pass it through the low pass filter, then it is very much similar as you are using a scaling functions, and you will get approximate coefficients. Whenever that signal or image you pass it through the high pass filter, it's very much similar to applying a wavelet function to our signal. You will get a detail coefficients. So ultimately as a low pass filter and high pass filter, we will be using the filter coefficient. In case of a Haar scaling function, we have seen that 1 upon root 2, 1 upon root 2. Those filter coefficients will be using as a low pass filter here to apply Haar wavelet. And high pass filter, that psi t functions we have seen in that G0 and G1, 1 upon root 2 and minus 1 upon root 2. These are the high pass filter coefficients we will be using to get the detail components. So now, I will stop here and then I will show you the Python program, how we can actually do it with help of a Python. This is image, so I will show you initially the signal. Okay. Basically, whenever you want to implement any wavelet transform in a Python, what you will need here is a Python library. Let me show you it here. That's actually a very good library available in a Python. That's called PyWavelets. That's for, you can use it, PyWavelets, for analysis, image analysis, as well as for signal analysis. So ultimately I am using the PyWavelets. I am importing the module of PyWavelet into my program. So initially what I will show you is the Debechi 8 wavelet I will show you. So what I have done here, import matplotlib.py plot as a PLT. Is this command and file is visible to all of you?
Yes, sir.
It's visible. Okay. So import pywt, that basically we are importing a Python, wavelet module into our Jupyter notebook. I am using basically Jupyter. You can do it with any IDE. You can also use Spider here, or many Python IDEs are available. You can use any one of that. I am using here DB1. That means Debechi's wavelet I am using, and I am looking at level 5 level of decomposition. So ultimately this program will plot a wavelet scaling function as well as wavelet sorry, I have given the different title. Actually this is actually wavelet function, not a scaling function. Okay. So we can call this as a father wavelet and this is a mother wavelet, right? If I take DB1 or a Haar, DB1 is very much similar to Haar. If I take DB1, what I will get here is a Haar scaling function and Haar wavelet function. That is your phi t and psi t. If I take more number of coefficients, my wavelet will become more smooth, right? So you will get a more smooth wavelet. So ultimately, these are the wavelets I am getting. I can, plot a different types of wavelets here by just specifying the name of wavelet here. Okay, and I am using this technique. Like I will be giving one signal. I will pass that signal to a low pass filter and high pass filter, and then I will get the approximation and detail. Further, I can pass this approximated signal to further level, again to low pass and high pass filter. I will get 2 more components and so on. So I can go up to any level. But in this program, I have gone up to the 4 levels. So I have specified level equal to 4. In this program, I have taken a sine wave with the help of a sine function. I have imported module from NumPy, that is numerical Python. I have imported, PyPlot from Matplotlib, so to plot the waveform. And I am plotting this sine wave, adding some noise into it. And after adding the noise, I am trying to remove the noise from it. So first what I will do, I will execute the program and then I will explain you. Okay. So this is what is shown with a red color is a sine wave with a lot of noise added into it. Right. So because I am using here, I have added here random noise. So noise is added into that. Then I am using wavelet decomposition. When I use the wavelet decomposition, it will decompose my signal into different levels. And then after, what I am doing, whatever the detail components are there, I am just simply making it 0. I am removing all the details because I know that here the noise is something like a very high frequency, and that's why I have to remove all the detail coefficient by making it 0. And after making it 0, I am reconstructing it again with the same wavelet. So whatever wavelet I am using for the analysis, the same wavelet I have to use for reconstruction. And when I will do it, it will try to remove all the noise from it. So whatever plotted with a blue line is nothing but a reconstructed signal, which is having much less noise compared to the original signal. So as you can see, you can also calculate the mean square error before wavelet transform was 0.082. Before wavelet transform means after adding the noise. Mean square error after wavelet transform is now 0.004. So comparatively noise is reduced after applying the wavelet transform. I have taken here a completely hard thresholding, but there are different thresholding techniques are available which you can use to get the better output compared to this output. So ultimately, this is how you will be able to decompose the signal and then apply, play with the coefficients, detail coefficients, and after playing with the detail coefficients, you can reconstruct your signal with help of a wavelet reconstruction. So in this Python library, very good functions are available. Wave DEC, that is for decomposition. Wave REC, that is for wavelet inverse transform, to reconstruct our signal back from the coefficients. Okay, is it clear to all of you? Some concept is cleared? Wavelet transformation, multi-resolution analysis.
Yes, sir.
Okay. So this is the one level of wavelet transform. Whatever shown in this slide is basically a one level of wavelet transform. You can go up to multiple level. Multiple level means further this approximated part, further you can divide it into 2 parts. Right? So like this. So you can have a wavelet transform with a filter bank method. If you use any input samples, let's call it as lambda 0k. Let's say we have a 1024 samples are available. When you pass it through the low pass filter, how many samples will be there at the output of low pass filter? Same number of samples, because passing through filter will not reduce number of sample, right?
Yes.
So the same number of filters samples you will get 1024 and 1024. But sometimes if your filter length is more, you will get it's possible that you will get more number of coefficient, but again you have to truncate. Whatever the coefficients you will be getting at the boundary, you have to remove it. So that your sample signal size should not increase. But if you do like this, the total number of samples will become double. So your signal size will be double. It should not happen. So for that, actually what we do here is a down sampling. So here we will perform a down sampling. So purpose of this block is to perform the downsampling. So because of that downsampling here, we will get, you know, a 512. So if you downsample it by 2, you will get a 512 sample here. And similarly, when you downsample this, you will get a 512 sample here. Why we are doing downsampling? Because we want to keep the same size, 1024. And of course, you don't require this many samples here because you have already passed it through the low pass filter. So now your bandwidth is half. So as per the Nyquist criteria, you know, you can reduce number of samples. There is not an issue because Nyquist criteria says that, you know, you should use number of samples greater than maximum frequency present in the signal. So your maximum frequency you're already making half. So there is no harm in doing the decimation process. So ultimately, whenever you do the filtering and downsampling in combined, it is known as a decimation, right? So after this downsampling by 2, you will get 512 here, 512 here. This 512 is a approximate coefficient. This 512 is a detail coefficient. If you consider these input samples as signal at V0 level, then this is at V minus 1 level. If you consider these input samples at V1 level, then this is at V0 level. Clear? Because we have removed some of the details from the signal. So ultimately, if I write it here, the levels here, then this is actually your, if you are considering this as a V1, then this will be V0 and this will be your W0, right? Wavelet subspace. And if then this would be your V minus 1 and this would be your W minus 1. Further, if you pass it through low pass filter, you will get here V minus 2 and here you will get a W minus 2 and so on. So there is no limit, you can do it at multiple level, right? Here if there are 1024 sample, here it becomes 512, here it becomes 256. So every time you have to do the downsampling. Otherwise, you know, if you do not perform the downsampling, your, you know, number of samples will increase, right? I think, is it clear to all of you?
Yes, sir.
Okay, if it is clear, let's
Yes,
go
sir.
ahead.
Okay.
Fine. Then how this wavelet transform will remove the noise, we have seen with help of a Python program. That wavelet transform is applied on the input noisy signal, and noisy signal is decomposed into approximate and detail coefficients. And then after, what we do here is we apply the thresholding to remove the small wavelets corresponding to the noise. And then we perform the inverse wavelet transform. Then after reconstruction, the noise will be removed. There are so many noise thresholding estimate techniques, like one of popular threshold estimation is given by Donoho. So people are using this equation to estimate the threshold level. Whatever the example I have shown, I have not used this thresholding, I have used the hard thresholding. That means I am making all the detail coefficients are 0. But actually it is a crude way of doing the thresholding, right? Otherwise, we have to use some soft way of thresholding. So L is number of samples under the process, and rho is a standard deviation of Gaussian noise. So depending on your noise level and number of samples under process, you will get the different value of threshold. This is one more example of multi-resolution analysis. 1024 samples are there. When you pass it through the low pass filter, you will get approximation component A1. You will get detail components D1. Further, if you pass this A1 to the next level, low pass filter and high pass filter, let me change the color of this slide, it's not visible. Let me take it red color. Okay. Then further you can decompose these into further approximate and detail part, A2 and D2. This A2 further you can decompose into two parts, A3 and D3. Now, if you are not interested in high frequency, if you are only interested in low frequency, then make all these D1, D2, D3 equal to 0 directly and then do the reconstruction. Then high frequency will not be present in the output signal. In case reverse, if you are interested only in high frequency components present in the signal, if you are not interested in lower frequency, what you can do, you can put approximation component equal to 0 and reconstruct your signal from the details component. Then you will get only high frequency component. So depending on your interest, what you have to do is you have to keep those coefficients and remove other coefficients. So that's the advantage we are getting after the multi-resolution analysis. This is one more example. If you have a noisy signal like this, then after wavelet transform you will get coefficients in this way. So initial part will be a low frequency part, and then after as and when you move towards this part, it is a high frequency part. So if you threshold all these high frequency components, and then after if you reconstruct the signal, you will get the pure sine wave back. If you are not interested in this sine wave, but if you are interested in this noise, then you can threshold this component. If you remove this component, if you make it 0, and then if you reconstruct, then in the output signal you will only get the noise. Original signal will be removed. So depending on what you want to keep and what you want to remove, you have to do the processing. There is one more example. This is speech corrupted with a Gaussian noise. After wavelet transform, it will look like this. And there are, small wavelets are there here. After thresholding, you can remove those small wavelets. Maybe those small wavelets are corresponding to the noise. Then in a reconstructed speech, you will find less noise. And if you find that, MSE, mean square error and all that statistical parameter will also improve. Now let's go switch to, because very less time is available. So now let me start the discussion of image processing. The image processing concept remains same. Instead of one dimensional, we are moving now in a 2 dimension. So that means in a signal we were passing the samples, in an image we are passing the pixels. So we have a pixels, let's say n by n. We pass it through the low pass filter. The filter coefficients are corresponding to the wavelet. Different wavelet will provide you a different filter coefficient. Let me complete this and then I will show you how to find out the filter coefficient. Okay, so you can pass this image through low pass filter and high pass filter of wavelets, and then after you perform the downsampling, because we don't want to increase the number of pixels, we want to keep the pixel size same. So let's perform the downsampling, and then after further level we can pass it through the low pass and high pass again. So initially we will, in a case of an image, initially we will process all rows. All rows we will pass through the low pass filter and high pass filter, and then once after that processing of one row is over, we will work with the columns. So again we will pass the columns through low pass and high pass filter, and at the same time we will be also performing the downsampling, because we want to keep the same number of pixels. So number of coefficients should be equal to number of pixels available in original image. So suppose if your original image is having n by n pixel, then in this approximate coefficient it should be n by 2 to n by 2. So ultimately this is called LL1 because our image is passing through two low pass filter. Low pass filter here and low pass filter here. So it is called LL1. Ultimately you will get an approximate coefficient. Then after LH, so you will get all horizontal details. Then after HL, you will get vertical details. And HH, you will get the diagonal details. So all four coefficients you will get approximate coefficients. Then three types of detail coefficient: horizontal detail, vertical detail, as well as diagonal details. All these details you will get once you perform the wavelet transform on the input image. And this is how it will look like. If this is your entire image, then during the first transformation you will get a CD1 here, detail coefficients for horizontal details. detail coefficients for a diagonal detail coefficients for a vertical detail, you will get here. And this is your approximation, which further you can divide with the same block. Further you can divide into 4. This CA2 further you can also divide into 4 in this way. So every time basically we are moving from V1 subspace to V2 subspace to V3 subspace, right? So whenever you are increasing the details, you are moving from the higher level. Similarly, see here, if you say that this is my V1, then this output will be a V0, because this V0 doesn't have a more details. So this is a V0, right? And this all three details belongs to W0. W0H, W0D, W0V, corresponding to horizontal, vertical and diagonal. And then this is actually a reverse, that is inverse transform. In an inverse transform, we use the reconstruction filter, reconstruction low pass filter and reconstruction high pass filter. And during the reconstructions, we perform the upsampling, right? So during the wavelet transform, we perform the downsampling. In inverse wavelet transform, we perform the upsampling. So ultimately, suppose we are here at V0 level, yes, you can go up to the higher levels also. And this is actually how you can do. If you have an image like this, you will be able to decompose the image into 4 parts, where this part will be your approximate part, approximate coefficient. You are passing through this image through 2 low pass filters. Then horizontal detail coefficients you will get here, diagonal detail coefficients you will get here, and vertical detail coefficients you will get here. So image will be decomposed into the 4 parts like this, right? So this is actually your coefficients of approximation. This is of coefficient of detail for horizontal. These are the coefficients of detail for a diagonal, and these are the coefficients of detail for a vertical. Further, you can also decompose this image into 4 parts like this. You can decompose further it in this way, and then you can also do the next level of decomposition. So in this case, we can say it is a 3-level wavelet transform, right? You can go up to multiple level in this way. Okay, this is one more, is a lung image, which you can see here that approximate coefficients is a lung. There are not much detail coefficients are available in this image. There is a 1 level of wavelet transform. You can further increase the number of levels. Let me show this in one Python program. Okay, so the file is visible.
Yes, sir, visible.
It's visible. Okay, fine.
Yes, sir, it's visible.
It's visible. All right. Okay. So this is what we will be implementing in a Python. So as you know, if you have a Python already installed in your PC, and if you want to install PyWavelets, then this is a simple command, pip install PyWavelets. Okay, still I am connected and slide is visible, because I am not getting it locally here.
Yes, sir. Yes, sir.
It's there, no? Okay, fine.
Yes, sir.
Okay, so if you are using Anaconda, then automatically PyWavelets will be there. No need to install. And if you are using an older version of Anaconda, you can also install it with the help of a conda command. Conda install PyWavelets. And if you are using some other IDE of Python, you can use PIP. That is, the PIP is a Python install. So it basically is useful for to install any module of Python. So PIP install PyWavelets you can use, as well as in Anaconda you can use Conda install PyWavelets. Right? These are the two packages you can use. Then if you are interested in knowing the families, import PyWavelet, and then I am writing here print PyWT families. Then you will find the different families available here. Har, Debye, symmetric wavelet, coiflat, biorthogonal, different wavelets you will get here. If you want to know more about the family, you can also print the list of family. So in a Debye, what are the wavelets available? So DB1, DB2, DB3, DB4 and so on. Ultimately, whenever you are increasing this number, that means you are increasing filter coefficients. In a DB4, 8 filter coefficients are there. In DB5, 10 coefficients are there. In a 6, 12 coefficients are there. In DB34, 6, right? So on. Similarly for symblat, biorthogonal and all that. Right? So this is how you can display the entire family. If you want to display coefficients, you can do it in this way. Okay, how much time I have now?
Sir, it's if it's about to end, then continue, sir.
Oh, okay, so I think by explaining this program, I think I will stop, right? After explanation of this program, I will stop, right? Is there any problem with next expert, or I mean, it's okay?
No, sir.
No, sir. You can explain.
All right, fine. Okay. So if we say if you want to display some coefficient values, you can say that W equal to pi WT dot wavelet DB2. So which is 2 wavelet coefficient. Basically, it has a 4 wavelet coefficient, like decomposition low pass filter, decomposition high pass filter, whatever we were talking about, this low pass and high pass, this filter coefficients, right? So these filter coefficients will be displayed. Similarly, it will display the reconstruction low pass filter and reconstruction high pass filter for a inverse wavelet transform. So when I execute this, it will give entire details. Family name is Debye, sort name is DB, filter length is 4. It has the orthogonal property, so orthogonal property is 2. It is also biorthogonal, so it is also true. It is asymmetric wavelet. And these are the filter coefficients displayed here. So these are the filter coefficients we will be using, right? If I change here now, instead of DB2, if I make it DB4, then I will get 8 coefficients in this way, right? If I write here DB8, I will get a 16 coefficients. So it will be multiplied by 2 basically. Whenever we are writing 8 here, it will be using internally 16 coefficients in that way. Okay. And if you see, I am doing here, a kind of a dot product to know whether filter coefficients are orthogonal to each other or not. So low pass filter and high pass filter, you can see dot product is 0. That means both are orthogonal to each other. And orthogonality is very important, because if there is no orthogonal filter we are using, it is very difficult for us to perfectly reconstruct the signal or image. So for a perfect reconstruction, orthogonality property is very much important, right? So both the filters, low pass filter and high pass filter, both should be orthogonal to each other. And then only perfect reconstruction is possible. Okay. This is actually a function I have written, although internal functions are available to convert color image into gray level image. If you have a color image, if you want to convert that into gray level image, these functions we can use. And we can read the image and then apply the wavelet transform. So DWT2 is for a 2-dimensional wavelet transform. If you do not use here 2, then you can use the same function for a signal. But this is a case of an image, so that's why I am using here 2. So it is basically a image. And I am using here DB1. All of you know that DB1 is nothing but a Haar function. If you want to display Haar wavelet here, I can write here DB1. When I write the DB1, I will get the 2 coefficients only. As I told you during the theory discussion, 1 upon root 2, 1 upon root 2, H0 and H1. And for a high pass filter, minus 1 upon root 2 and 1 upon root 2, that is G0 and G1. So these are the filters. Either you can use here a Haar filter, or you can use here any higher level, right? If you require a fast computation, then you can go for a Haar wavelet. If you here increase the dB, instead of dB1, if I write here dB4, dB8, or any other bi-orthogonal wavelet by specifying bi-or 1.3, I will be using more number of filter coefficient. I will be getting better result, but maybe that my computational time requirement will be higher. So ultimately this function will give me the coefficients in the form of approximate coefficient, horizontal coefficient, vertical coefficient, detail coefficient, and so on, right? So ultimately what I will do, I will run this program. When I run this program, what it will do, it will give me the approximate coefficient, horizontal coefficient, diagonal coefficient, and vertical coefficient corresponding to this diagram, right? Approximate, detail horizontal, detail diagonal, and detail vertical. So this is what I am getting. Further we can apply DWT further on this. Now what is the advantage here? You can see that there are no details available in vertical, diagonal, and horizontal coefficients. So suppose nowadays people are actually using deep learning algorithm to identify whether it is a COVID-19 patient or not. So for that purpose you have to use lot of database images, and if the size of database image is very large, you will require a lot of storage, as well as your processing time will be also more. So it is better that whatever is not important you remove it with help of a wavelet transform. So it's better that you apply 3-level wavelet transform, and whatever you are getting approximate component, smaller one, that you fit to your deep learning algorithm. Your deep learning algorithm will work very fast, and your storage requirement will be less, processing requirement will be less, and most of the energy is already available in this approximate coefficient. So that is one application. Another application, that sometimes you are interested to find out the details, what is the details available. Then you can also look at the detail coefficients. So those details will be easily visible in this part actually. So to show that, actually I will show you one more example. This again I will run. What I will do here, quickly I will show you this original image, and this is a reconstructed image. So in this reconstructed image you can see the vertical lines are missing. No vertical lines are available, because what I have done, the coefficients corresponding to vertical line I have made it 0, and that's why that is not available in reconstructed image, right? So because I have all the coefficients available in this tuple, and I have made coefficient corresponding to vertical equal to 0. It is there in C11 tuple. Let me try this. Instead of making C1 1, I will try 1 0 and 1 0 here, and then let me run this program again. Now you will find that now horizontal lines are missing, only vertical lines are there, because I have removed all the horizontal detail coefficients, and that's why horizontal lines are not there. So depending on what type of analysis you require, you have to play with all these wavelet coefficients. When you play with all these wavelet coefficients in a reconstructed image, you will get a different details. I think my lecture will go on continuously, but somewhere I have to stop. So I will stop here. If you have any doubt, any questions, you are free to ask.
Any query, participants?
Should I stop sharing the presentation?
Sure, sir.
Okay,
sure.
okay, because I am bad in time management. I could not complete my entire presentation in time. Okay.
Yes, sir. No one has any queries.
Okay, okay, fine. Thank you
very
so
much, sir, for explaining us. Sir, we have been receiving comments. That's a very nice explanation, sir, from the chat box. So I just wanted to convey you.
Thank you very much. Thank you very much. Okay.
And one of our EC students is Tamal Ghosh. He has said it was an awesome lecture. So
Fine.
thank you so much,
Thank
sir,
you very much, Tamal.
for
Thank you.
sparing your time and yeah.
Thank you, sir.
Thank you to
Thank you
Pathak
very
also. Pathak, I can see one message from Pathak also, right? Okay. Thank you very much. Thank you very much to all. Bye.
Yes, sir.
Goodbye. Goodbye. Yeah.
Thank
Thank
you,
you, sir.
sir.
Goodbye, sir.